To talk about amplitudes and Wilson loops in twistor space.
Oh, is it working? Yeah. Hi. So, well, I'd like to thank the organisers for inviting me here to Cambridge, which is looking, as usual, spectacularly beautiful self with the daffodils and everything, and to come to this exciting meeting. So, what I want to talk about today are amplitudes and Wilson loops in twistor space, and just more generally, I was asked to give a more pedagogical talk, and as such, I should apologise to the kind of more expert people here who will have heard this before, and but one should never try to appease the experts in a lecture. So this is based on joint work with Tim Adamo, Matt Bullimore, and David Skinner. So David Skinner going back a long way, and Matt Bullimore, who's here in the audience somewhere, so he can fall asleep anyway. Okay, so I just want to start with some general comments, and so over the last few years, there's been a remarkable range of applications of twistor theory to amplitudes, and it's maybe I thought I'd just most of this talk will actually really concern one corner of this, but twistor space actually has been applied to amplitudes now in many really quite distinct ways. So traditionally, so this is going back to the 60s, the heady days of the 60s when twistor theory was new. Roger Penrose introduced twistor diagrams, and Andrew Hodges has been sort of valiantly carrying that banner for the last 40 years or so. And recently they've made spectacular progress, but I won't talk about that. But what really changed the game was Witten's twistor string theory. And so Witten's twistor string theory was, as many of you probably know, you put a string theory into twistor space, and lo and behold, you can calculate scattering amplitudes for ordinary conventional theories, both for Yang-Mills and, well, I've said gravity there, but it turns out that it's conformal supergravity is what most naturally comes out, and so despite the fact that twistor strings were the most kind of radical and maybe promising way of calculating amplitudes, there was no way to extricate the conformal supergravity, and so whilst it gives some beautiful formulae at tree level, it's unclear how to make them do anything for you at loop level. And the string calculations would in fact be quite challenging at loop level. So the program that I engaged in was to really extract from twistor string theory what was applicable to the straight Yang-Mills, but you could, if you write down an effective action that comes out from the string theory, then you can separate out the parts. You can get rid of the bits you don't want, and so the twistor actions could be applied to understand amplitudes both for Yang-Mills and gravity separately, if you so desire. But there are various other things that I won't talk about today. So there's the twistor Grassmannian, as developed by Nima and Nima Akani Hamid and Freddie Casciazzo and friends, so to speak. And there's actually two Grassmannians. There's a twistor Grassmannian and there's a T-dual momentum twistor Grassmannian. These are quite different animals. So in fact, this is the more powerful one, but this is the more fundamental one. So these are things that correspond to what you get when you think about, in some sense, this is what you get when you think about a Wilson loop, and this is what you get when you think about an amplitude. And there's a non-trivial transformation between them. And finally, one should say that the strong coupling approach also sort of uses twistors in an auxiliary sense, in the sense that the lax pairs are represented on twistor space, and the boundary data is encoded into momentum twistors as well. So there's a kind of a loose tie-in between these things. And of course there are interrelationships across the diagram, but they're not as strong as one might expect or like. I mean, one can understand the twistor Grassmannian somehow is coming out from a twistor string representation of leading singularities and such like. Okay, so the top row here are all frameworks involving twistors that have some version for gravity. The bottom row is to a large extent dedicated to Yang-Mills, or n=4 super Yang-Mills, although as we've seen in Arthur's talk earlier and maybe in Yutin's talk tomorrow, that there is some progress with some of these ideas for ABJM as well. So the gravity story is much less developed, and I probably won't have time to talk about it, but that progress is being made on all these three different fronts here, but that would be the subject of another talk. So what I want to talk about today then is the application of these, really the methods centered around the twistor action to studying the S matrix and correlation functions, particularly of Wilson loops, and the S matrix Wilson loop duality. One of the things that Marcus said in his talk yesterday, his very beautiful talk yesterday, was that of course these things are so good and so wonderful because they're on shell and they they're sort of essentially non-local and so on. What I want to the point that I want to make is that in fact all of these ideas have a perfectly good off-shell representation arising from an action, but the action is not local; it's a twistor action, and so my spin on this would be that in fact it's the twistor theory that's generating the simplicity we're seeing in these modern methods, rather than the fact that one's really working on shell or with recursion. Although one can take, well, I mean, all these different things play a role. Okay, so what I want to do then is to give you an overview of how the twistor actions can be set up and how they come about. And first of all, I need to tell you what twistor space is. It may be best to actually have some sort of picture. So twistor space is just C4/4, so you have 4 bosonic variables and 4 fermionic variables, and it's a fundamental representation of the superconformal group. And we tend to coordinatize it with so the 4 bosonic components would be denoted Z alpha, and the fermionic components chi A, and these indices go from 0 to 3, A equals 1 to 4. And in turn, we often break up the 4 bosonic components into 2 two-component spinors. And I'm afraid it's just a habit of mine to use Penrose notation for the indices. So these are 2-component. But I won't use too many indices. So if you're allergic, then then you can ignore that. And the main way to think about how they relate with space-time is via the incidence relation, where so the incidence is with points in chiral super Minkowski space. So this is so we only are going to consider thetas and not theta bars, and the incidence relation is thus given by mu a prime equals I to a prime lambda a chi a theta a. And the way you think about that geometrically is that you might have a point x in space-time. I'll suppress the theta in general. And sorry, the other thing I didn't say here is that we usually like to think about the projective space, which is what we get if we take out the scalings. So this is a 3/4 dimensional space. We've taken out a bosonic scaling, and we can think of lambda a as coordinates on a Riemann sphere, as homogeneous coordinates on a Riemann sphere. So that is to say that the ratio is thus a standard affine coordinate on the complex plane. And so a point corresponds to a line in the twistor space, so parameterized by lambda. So so this is space of x and theta. And the main thing that you need to remember is that 2 points are null separated if the two corresponding lines in twistor space meet at a point. So twistor space encodes the conformal structure of space-time just via incidence. This, of course, all works bosonically, but for the applications to super Yang-Mills, we will want to have everything working in this supersymmetric framework with thetas. So that encodes the geometry in twistor space. A point in space-time corresponds to a Riemann sphere in twistor space. How do we encode massless fields? So to start off with, I'm going to want to think about Yang-Mills as a multiplet. So n equals 4 super Yang-Mills in twistor space. Well, to start off with, on space-time, we will have a multiplet which consists of a connection, a spinor, a bunch of scalars, a spinor of the other type, and so here this is omega 1 with values in the Lie algebra sum group, and this G is going to be thought of as the self-dual, anti-self-dual part of the field. So this is in omega 2 minus the two forms that are anti-self-dual, values in the Lie algebra. Well, everything takes values in the Lie algebra. And then these are the scalars, and these are spinors. These are plus spinor and minus spinor. And so on twistor space, so these are sort of tensors of different degrees, or at least one form or two form spinors of each type. Whereas on twistor space, these are all going to be 0-1 forms. So this corresponds to, in fact, a superfield A, which are a 0-1 form. So that just means that on twistor space, and so this is only going to be just bosonic components to the 0-1 form, and it has an expansion though when you in the fermionic coordinates, chi times psi plus chi squared times phi plus chi cubed times psi tilde plus chi to the fourth times g. And each of these is now a bosonic 0-1 form on twistor space, and so A corresponds to A, etc. And there's an example of how you actually realize this you can write down an integral formula. Phi is the integral over the line x of the little phi times d lambda. Well, d lambda is just a one form, holomorphic one form. So phi was a naught one form. This is a one naught form. Because it's coming at the second with a chi squared. This all has to have homogeneity degree 0. Chi squared has weight 2. This has to have weight -2. So this all makes sense as an integral, and you can read off the phi just as an integral formula. And there are corresponding formulae for the psi, tilde, and the g, and the a and the psi, but maybe a little bit more complicated, which so I won't go into them. The so the action on space-time is sort of familiar to most of you, but I'm going to divide it into two parts. So so the Yang-Mills part is going to have a BF form, although here I've called it G. Maybe I should have called it B. So for G read B, and I'm going to write down an action that gives rise to the oops, I run out of space here. Plus psi squared phi. So the point of this action is that if you vary this action, you actually get a self-dual, you get an n equals 4 extension of the self-dual Yang-Mills equations. And you can see that as far as the Yang-Mills part is concerned, because this G was anti-self-dual, you vary the G, and that tells you that the anti-self-dual part of F must vanish, so F must be self-dual. So this isn't the full Yang-Mills action, and you had to add on an extra term, and this is where G squared is going to go, and this has a G squared over 2 plus psi tilde squared phi plus phi to the 4th in the so if you add these two together, then you get the full Yang-Mills action with the G squared as the coupling constant in front of the term that takes you away from the self-dual sector. So, okay, so that's the space-time super Yang-Mills action. And on twistor space, well, so going back to 1978, Richard Ward had a construction for self-dual Yang-Mills fields in terms of holomorphic vector bundles. Holomorphic vector bundles are defined by a d-bar operator, which is so here, of course, we're all used to the idea of a connection on the bundle over space-time, d plus a. On twistor space, you have a similar thing, except it's defining what you mean by a holomorphic section of a bundle, and the self-dual part of the action is the so self-duality corresponds to F02, which is d bar plus a squared, equals 0. And so on twistor space, the action that gives rise to that equation is just a Chern-Simons, holomorphic Chern-Simons action, plus 2/3 a cubed d3/4z. Okay, so that's the self-dual part, and so I guess everyone's familiar, perhaps, I hope, with the fact that the variation of this action tells you that the curvature should vanish. That's telling you that the F02 part of the curvature should vanish, and it's a holomorphic vector bundle. The interaction term is then has a rather more obscure presentation. So this, well, we have our g squared, and what we do is we write down an integral over space-time of the log of the determinant of the d bar operator, d bar plus a, restricted to the line. And so to a sort of classical geometer or a classical mathematical physicist, this probably looks like a rather horrid term to have introduced, but to a string theorist, it's of course rather natural. It's the effective action that you would get from coupling d1 instantons to well, I suppose you'd call it a space-filling d-brane or a bundle, and you're just integrating out some fermions on the Riemann sphere X, and you get this log det term. And in fact, for a string theorist, this term is rather familiar as well. This is the holomorphic Chern-Simons theory that you might have expected to get from some B model in twistor space. So this twistor action together really is a relatively straightforward expression of Wisson's B model coupled to D1 instantons, but as an action principle, as an effective action. And what this allows us to do is to essentially decouple the conformal supergravity, because what we're going to do is we're going to use the kinetic operator just associated with the A here to define the propagators, and there'll be no conformal supergravity running in any of the amplitudes that we deal with. Okay. So then the question arises as to why is this helpful, and why is this division of the action into two parts helpful? Well, the point is that the self-dual sector is integrable, and in fact has no scattering. So it's quite natural to try to expand around the self-dual sector, and we've set up the coupling constants and such like so that we can do that. And so how do we express this in a way that's going to be something that we can calculate with? Well, on space-time, if you wanted to reduce the self-dual sector to a trivial action, well, if you look at it, there's really no way you could do it. I mean, there's a lot there in that self-dual action that's non-linear. You can't just do a gauge transformation on space-time that eliminates psi squared phi, for example. It's just not an available gauge transformation. Whereas on twistor space, you can. So how can you do that? Well, I should say that there is a gauge in which you can take this twistor action here and term by term gauge fix and integrate out the fermions and get yourself down to those two terms separately. I mean, this is just a direct calculation. But anyway, so to make this explicit, by choosing an axial gauge on twistor space, and so to do that, we'll just choose a constant twistor, which I'll thus denote by Z star, and set Z star. So this can just be a bosonic twistor. Just set one of the components of the potential equal to 0. Now, morally speaking, I mean, I've set twistor space up with 4 bosonic coordinates, but we projectivize. So in fact, it's really a 3-dimensional space. And so what we're saying is that one component of the form A is 0. So A cubed must vanish, because it only has 2 non-trivial components. So the self-dual part of the action is going to be just A d bar A. And so what we've done with this gauge transformation is we've trivialized the self-dual action. We've turned it into purely kinetic terms, something that you would not be able to do on space-time. The other good thing, though, is that when you look at the propagator in this gauge, this becomes something geometric. So it turns into delta functions. So I'll denote the delta functions by delta bar 2/4, and the point is going to be that the well, what does that mean? Well, this is support where the 3 points Z prime and Z star are collinear. And the so just to be a bit more, to actually define the notation, the we can write delta bar 1 of a complex variable Z is just d bar of 1 over Z, 1 over 2 pi I, or the delta function of the real part of Z, imaginary part of Z, times dz bar. So this is a 0-1 form. And for a fermionic coordinate, it's just the fermionic coordinates itself because of the relation, the Berezin integration relation. So something like delta bar 2/4 is going to be defined just by integrating out the delta function, which so we're going to have, say, Z plus S times Z2 T times Z3 ds dt over ST. So it's integral over C cross C. So the point here then is that this delta function has support when its argument vanishes. If you integrate out over S and T, then what you're discovering is that Z1 plus Z2 plus TZ3 must vanish for some value of S and T. And you can see that it morally has poles when 2 of the points come together. So this satisfies the well, I don't know if I need to write this out, but we can Z1, Z2, Z3 is a sum of the 3-dimensional delta functions which tell you that the pairs of points are it has poles when the pairs of points come together. Okay, so that gives you the propagator, and so we end up with a very simple propagator. The thing that looks like it might be a nightmare is the vertices that will come out of this log det term. but it's there, and we have to deal with it, and we'll see that it's actually not as bad as you might have thought. So, so what we get then is well, there's a standard expansion of the logarithm of the determinant as a trace of Green's functions for the operator times the variation in the operator. So we get a expression for the vertices so it's a sum over n, so it's d4/8x of trace pi a and so the nth term here is a product of n objects. This will give rise essentially to the nth an nth vertex, and in this we're imagining the line x. It corresponds to z of sigma equals, say, z a plus sigma times zb. So we're representing the line x that we're integrating over there in terms of that kind of representation. Okay, so this gives you a whole bunch of a sequence of vertices, one of each order n, and this rather simple propagator. And you might then say, well, what is this? So this is a Feynman diagram calculus for n equals 4 super Yang-Mills. So we can translate to momentum space. So there are simple formula for wave functions that are defined on momentum space. So with momentum pi equals lambda I, lambda tilde I, eta I for the these are spinors, two-component spinors of each type. That's an A and A prime, and this has an R symmetry index. And we can write AP. Well, if I rub out the particle number there, and then we can put API is equal to integral ds over s of s lambda minus lambda I exp. So we can plug in momentum space at every point, and we discover that Vn a P1 up to APN is just, as you might have expected, the MHV amplitude. So so what we discover is that the vertices are essentially the MHV amplitudes, and we can do a similar trick to translate the momenta into, the propagator into momentum space, and we discover that we get a scalar propagator. So delta z prime corresponds to 1 over p squared But we have delta functions that are telling us that we have to make the lambda proportional to the well, there's an iota times p. If that's the best, I'm not sure that's an ideal notation. Well, the point is this delta function is telling us that lambda has to go to p times iota, where iota is part of z star. Okay, so what this does is it gives you a formalism where the vertices are the MHV vertices and the propagators are the standard 1 over p squared, but with a prescription that tells you how to make the momenta in the propagator into a lambda for plugging into the vertex, which is the MHV rules. So this is, of course, already well known from twistor string theory, and but this gives you a derivation from Lagrangian principles. And as we'll see later, this derivation allows you to apply this to anything that you'd want to compute in quantum field theory, like a correlation function or a Wilson loop and such like. So it's worth mentioning that, so what I was saying before was that the simplicity that people are seeing in amplitudes is in this language coming from twistor space. And so when Marcus gave us these examples of things which are very, very simple, it's worth, well, the thing that really drives simplicity, so it's very efficient because the number of vertices is equal to the loop order plus the MHV degree plus 1 in a diagram. Diagrams for n to the k MHV at L loops. So n to the k MHV just means that i.e. k plus 2 minus particles. So it's the k counts the number of minus helicity particles, or k plus 2 does. So what that means is that in particular, the number of vertices doesn't depend on n, as it does in a normal perturbative scheme. And for low L and K, you get very few diagrams altogether. So for Marcus's example of the one loop next to MHV, there's only one class of diagrams. And so he had a very neat expression with just 3 terms. So the MHV rules are maybe going to give you a few more than 3, but they'll be all of the same type, and there'll be sum over permutations. And maybe you can have a few more legs on one and the other. And when you get down to 6 particles, you'll find that many of those are vanishing, so you do get a simple expression. So you're not getting the 30,000 terms that you get from a normal Feynman diagram analysis. And that's really coming from the fact that you've set to 0 all of the nonlinearity in that self-dual part of the action. Okay, so the Feynman diagrams allow you then to calculate amplitudes according to standard rules. It gives rise to this well-known formalism, the MHV formalism, which I guess the Queen Mary group here famously showed actually worked at one loop despite its origins in twistor string theory. So so what I want to do now is to explain how this can be used to calculate correlation functions and Wilson loops. So the point is, though, that if you want to calculate a correlation function, essentially all you need to know is what the contraction is, AZ1, AZ2, and in this gauge, we're just going to get the propagator in a normal way, or the time Z1, Z2 star. So this is a rule that can be inserted into any prescription of operator. In fact, it would be helpful for me to describe how to build the Wilson loop first, because it has ingredients in it which you need to describe ordinary operators like scalar fields and such like. So to give some motivation, I should remind people of the S-matrix Wilson loop duality. Well, at least remind some, a number of the initiators of the ideas are in the room, or these people who provided the crucial evidence. And so this is so the idea here then, oops. So I guess it's, sorry, I'm not sure whether I really want to DHKS. I'll spell out the names of those in the room, I suppose. Well, I get a bit lazy, actually. I'll just do BST at the bottom. I hope you don't mind. Just okay. So the sorry. Sorry. I suppose, well, anyway. No, it's fair. Okay, so the idea here then is that if you're working in the planar limit, so SUN, n goes to infinity, the we just look at the leading trace parts of the amplitudes, and this gives us an ordering on the diagram of the ordering of the particles taking part in a scattering process, and the momentum conservation tells you that if you just follow all the momentum round, adding them end to end, you end up where you started. And this leads now to a, actually I never know whether to have this x2 and x1, but anyway, I'll start this way. I'm probably violating my own conventions now. We can put in, we can define region momenta and in fact, these can be supercoordinates xi, theta I, such that pi, eta I, so the supermomenta are just the differences, xi minus 1, theta I minus 1. So in fact, Andrew Hodges had already done quite a lot of work with amplitudes in this format, where this x and theta was the space-time, and had already spotted some rather extraordinary structure. Unfortunately, I don't have time to talk about that, but it's anyway, but the main conjecture was that, and this was at least initially expressed just for the MHV amplitude, that the S matrix at weak coupling is equal to the correlation function of the, well, sorry, this is a conjecture that's actually made to all values of the coupling. So the S matrix divided by the MHV tree is equal to the Wilson loop, the correlation function of the Wilson loop. And this is remarkable in the sense that you're talking about scattering for n equals 4 super mills and for the Wilson loop in the same theory, but on a space now where the x's are somehow more closely related to the momenta. Now, geometrically, we can encode this polygon in twistor space quite straightforwardly. So if this is the polygon with n sides, then so Cn corresponds to a C tilde n in twistor space, because the each of these points, vertices here, and this is a genuine geometric duality, so it's a duality used in its old-fashioned projective sense. The so here the point x1 corresponds to a line, x2, x3, and these lines meet at points because P1 is a null vector. So xn is on the light cone of x1, and that means that the two lines are incident. So so there's xn, and this is going to be z1, which in some sense is related to the momentum p1, and z2, z3, and so on. So, so geometrically, the polygon in region of momentum space defines a polygon in twistor space. But what's rather nice is that the polygon in twistor space is now unconstrained. The polygon in momentum space, the sides had to be null, and this is a bunch of rational conditions, whereas in twistor space, the vertices here can be freely chosen. And this in itself has actually been a great boon to people working in the field, that the algebraic relations are not, that there are no algebraic relations that you need to look after. If you express your function as a function of n momenta instead of a function of n twistors, then the algebra, you don't need to worry about two inequivalent representations of the same function. This is again something that Marcus referred to. And okay, so what we want to do is, if we want to say something in twistor space about this conjecture, we need to talk about what a Wilson loop is going to be like, and sort of figure out how to actually compute it using these Feynman rules that we've just been discussing. So on the line xi, we can write down z is z of a general point, z sigma being z I plus sigma zi minus 1. Well, I've got zi plus 1. And now, you see, on space-time, what you'll be doing is you'll be forming your observable by taking the trace of the parallel propagator around the polygon. Here, you've got to think of some way of carrying some vector in your vector bundle around this polygon, and there isn't really a connection on twistor space. There's this d bar operator, and on a line in twistor space, what you discover is that at least for, perturbatively, a vector bundle is always trivial on a line, and that means that you can solve for a solution to the condition that a section of your bundle is holomorphic globally over a line. So that so E is trivial on lines. So there exists a solution, and in fact it'll be a unique solution with the appropriate boundary conditions, d bar plus a restricted to x of u x sigma equals 0, with say u x 0 equals the identity. And there's a formal solution here that you can write down, but I guess the point is that the analysis is straightforward, so you can write down a perturbative solution, 1 plus sum n equals 0 to infinity, integral over n copies of the line of sigma minus sigma. Well, sigma 0 here is 0, but I seem to have pi. So there's anyway, there's an integral formula, and in fact it's no worse than the sort of things that we've been dealing with in the study of the MHV amplitude. It's a product with these kind of Park-Taylor type denominators. So what this does is it tells you how, given a vector here, to say what its counterpart is around here, and then you can carry on round the polygon. So we can define Wilson loop in twistor space then as being just a trace of the products of these U's. Now, okay, so this gives you a well, that's another step. So this gives you a definition on twistor space, and you then might ask, well, what is the connection between this and a corresponding Wilson loop on space-time? And well, there are some peculiarities here because, well, maybe the easiest thing to say is that if you work without supersymmetry, then the answer is that this is just the Wilson loop on space-time. And this follows from an extension of the Ward construction. Certainly it's true in the self-dual sector that this is just the Wilson loop on space-time. But what's peculiar is that the space-time and supersymmetric analog of the Wilson loop requires the field equations, requires to be on shell in order to be defined. There's ambiguities in its definition otherwise. This is a completely off-shell definition. But this gives an off-shell definition of a super Wilson loop. Oops. So so you can now start calculating the correlation function and just see what you get. And what's rather remarkable is that well, I suppose I should just state this as a result. I mean, you can see what's the first thing that you would get. You would get you just look at a propagator coming across here. You're picking up an A from there, an A from there. You're taking the so the leading order part is just when you have an expression that depends on a contribution from one side, contribution from another side, and you substitute in the propagator. You integrate it up and down both those lines, and this gives you a rational function of the twistors. Which is has a relatively simple form. Well, if I just write the 1, 2, 3, 4, 5, this square bracket is the basic R invariant. I'm not sure whether I really need to write it all out. It's Z1 chi. What is it? Okay, anyway, so this, trying to persuade you here that it's a simple formula. These are just skew products of four bosonic twistors, and this is the fermionic part. And this is what you get just by integrating the, you could think of this also as a delta bar 0/4 where you've integrated out another two parameters. (2/4) Z1 Z2 plus S Z3 Z4 plus S Z5 plus T Z5. Sorry, maybe I don't need to go into this. Anyway, so this gives you the MHV amplitude on the nose by adding up contributions like that, and you can. So the statement then is that the 4D planar loop integrand equals for the S matrix, for n equals 4 super Yang-Mills S matrix equals the 4D loop integrand planar integrand of the Wilson loop. And the the first way to understand this is just by looking at the diagrams directly. So the direct method is just to so you look at the Feynman diagrams for the Wilson loop. Are the planar duals of those for the for S matrix, and the and you discover that there are peculiarities in the so that in itself is a curiosity that you get this planar duality, but then you also discover that the expansion in the coupling constant is the loop expansion. So the expansion in the coupling constant for the Wilson loop is the loop expansion for the S matrix. So in particular, the tree level S matrix equals the Wilson loop evaluated in the self-dual theory, i.e. G equals 0. And the loop expansion in the S matrix equals the expansion in G squared for Wilson loop. And there's a fancier way to prove the equivalence was done by Bullimore and Skinner, who showed that the loop equations imply factorization. So that is to say that if you deform your Wilson loop, and you can imagine this as a BCFW deformation, so you start shifting one of these lines, maybe you just move it along another line, at some point it's going to, as it comes along, it's going to hit another line there, and that corresponds to when the momenta sum up to 0, some subset of the momenta sum up to 0, and that's where you get a pole. So the loop equations were used in ordinary Chern-Simons theory to tell you when what happens to the Wilson loop as the two lines cross, and in the topological case you just get a jump. In this context you get a pole. And anyway, you obtain factorization, and that gives rise to BCFW recursion in the all loop sense. Okay. So this gives a nice proof of the Wilson loop S matrix correspondence, albeit at this sort of four-dimensional loop integrand level. What else can you do with this calculus? So I guess it's been taken further in two ways since. One way is to study more general correlation functions. So, and you see, one of the features of the twistor approach is that it incorporates supersymmetry automatically. So your notation doesn't need to tell you about what's happening to different components of your supermultiplet. That they're all sitting in a generating function, and so you can study supersymmetric correlators with no pain. And so what you can do here then is you can look at the sort of correlators that Grisha was telling us about this morning. So first of all, you need to know how to define the scalar field. Well, I wrote down the integral formula before, but in fact I wrote down a rather simple one, which was only really valid for the U1 gauge theory. And in fact, it turns out that if you want to work out, so here this is actually going to be a superfield. This is actually a fermionic curvature. So it leads on the scalars, but then the theta terms are natural supersymmetric completion. And this is given by an integral over the line x of this same function that we were dealing with before that trivializes over the line. So we need this extra, so to speak, parallel propagator term in the game. And so we can then sort of, using the same methods as before, using the expansions for U, write down the loop integrand for the correlators for these things. And so we get an MHV formalism for the loop integrand of the correlators. So you know, if we defined our OX to be just trace of phi, I mean, it's usual to look at the BPS case where there's no summation, no sum over AB. So we can then look at some endpoint correlator, and this also gives rise to, you see, when you have this formula here, one of the things that you can that one can do is there's this correspondence with the S matrix, or with the Wilson loop. It's probably easiest to talk about this in the context of the Wilson loop, by letting points become null separated. And so I guess Grisha talked about this a bit this morning. So if you well, maybe the exact formula is going to be that the Wilson loop equals the limit as xi minus xi plus 1 squared goes to 0 of this multiplied by xi minus xi plus 1 squared. So, so you can see this correspondence arising by virtue of the fact that the non-trivial, you know, you've got to cancel these zeros here, the xi minus xi plus 1 squared, and that those will only happen when these when the d2a by dx dx in the definition of OX contract with each other around a polygon. So this is just an endpoint correlation function. The points are not distinguished in any particular way, except the ordering of a polygon is given to you there. And when the sides of the polygon become null, which is what this limit is doing, the actual d2a by dx dx cancels out, and you get left with just the u's from the Wilson loop. It's really squared, isn't it? But I guess okay. So so that was one direction. Sorry, I'm running out of time, aren't I? The I'll have to be very brief indeed with the other directions. So you can worry about sort of anomalies and things, and it's always an interesting question to ask how anomalies are realized and whether you can exploit them in some way. And this is Matt and Dave again, but also, I guess, CF Song and Simon Karen Huat. You can ask about the anomalies of the Wilson loop under supersymmetry transformations, and they get sort of what they call descent equations, where you look at what happens under Q bar. So Q bar is actually acts anomalously on the Wilson loop. In some sense, there exists an ambidextrous Wilson loop, which Q bar actually preserves, but this is pulling out part of that fictitious Wilson loop that's not really there. And this equation tells you that if you look at the end particle, the endpoint Wilson loop as L loops with MHV degree K, well, I mean, the best I can do in the time available is to really tell you to go and talk to Matt if you want more details. Q bar hook D3/4Z. So Q bar is a vector field on twistor space. This gives you a 2/4 form that you can integrate against. But basically what it does, it tells you that the Q bar variation of the Wilson loop is given by the integral of a Wilson loop with one lower order and one lower loop order, but one up on the MHV degree. And so in principle, this could be used to sort of bootstrap a construction of the Wilson loop at high loop orders if you know everything you wanted about the low loop orders. And, and the tree level is, of course, very well understood. I mean, there are some technicalities there, and there have been some successes as well. And as I say, I recommend you talk to Matt if you want to know more details about that. So actually, yes, that's right. I have the luxury of a few more minutes. So, so I could just make one or two words. So I'm getting rather sort of telegraphic here at the end, but I suppose if I have got a few minutes, I could just say a few words about gravity. At risk of changing the subject completely. So, so what is the status of gravity in all of this? So, as I said at the beginning, the whole story was in some sense, what is the twistor string story, was in a sense fouled up by conformal supergravity. And, but therein lies an opportunity, because well, so first of all, in the same way that you can write down a twistor action for the Yang-Mills part of the story, you can so first of all, there exists twistor string theory for conformal supergravity. So I'll call that C-sugra. And you can abstract from that in much the same way as we did the Yang-Mills case, a twistor action. And so there are, you can play the same games. You can write down an MHV formalism, for example, and you can write down string formulae for the scattering amplitudes. And I guess these get very complicated, and not much has been done there. But also, one of the reasons for that, of course, is that people aren't very interested in conformal supergravity. It's a notoriously sick theory, or at least in the way that people currently understand it. And I think it has one or two adherents still. But there's also an opportunity in the fact that Einstein gravity sits inside conformal supergravity. And indeed, this was in some sense the motivation for an attempted Einstein twistor string theory that Chris Hull, Mohab Abuzaid, and I wrote down several years ago. But that was sadly incorrect. It only gave the self-dual sector. But recently, Maldacena has come up with a rather nice argument, and just in a nutshell, the Maldacena argument is to observe that if you take the action of conformal supergravity, well, no, actually, in his case, it's just conformal gravity, C grav, then he didn't quite say it like this, but if you restrict it to an Einstein solution, Einstein data, then it's equal to the, and now it's Einstein with cosmological constant. It's equal to lambda times the Einstein gravity suitably renormalized. So if you imagine yourself in de Sitter space, so what you see then is that maybe an explanation for why it was difficult to produce a twistor string theory based out of the embedding of Einstein gravity and conformal supergravity with zero cosmological constant, because you are going to get something trivial if you're not careful. Now there is, as I say, a twistor action, and we can use this to, and a twistor string. So the point is that if the cosmological constant is not zero, what this means is that we can use the twistor string formally for conformal supergravity amplitudes and construct the Einstein supergravity amplitudes, which will have this spurious factor of lambda in it. So we have problems taking lambda goes to zero, but if you're calculating amplitudes, your amplitudes are polynomials in lambda. So you simply need to divide by lambda and look at what's left, and that will give you the Einstein amplitude. And also, by the time you're looking at the twistor action for conformal supergravity, you can extract this factor of lambda by hand, and you can get a twistor action which will apply directly to Einstein gravity. So this is currently work in progress with Tim Adamo. And so, in particular, an upshot of all this is that we should be able to provide a proper, when I say a proper ontology for an MHV formalism of gravity. Proper is probably in the eye of the beholder, but one that satisfies me, but I guess people will probably want to see some consistency checks and such like. Okay, so I'll finish there then. And so anyway, so I think we're seeing some sort of, we're beginning to see some rapid developments in the gravity direction now after several years. So thank you very much.
Questions?
Is this argument only for tree level, or?
Well, yeah. So it would certainly only be for tree level for the twistor string formally, because the problem with twistor string theory is it just gives the whole theory at once, and if you don't have a scaling parameter to sort of decouple parts of the theory, then you're going to get the conformal supergravity modes running around the loop. In the twistor action, you can say, well, I'm going to use the Einstein propagator, the Einstein particle propagator, and so then you know that your loops can't have any supergravity modes running around them because you've only used an Einstein propagator. So the point is the twistor actions give you a kind of a much more control over what it is that you're computing. So, I mean, obviously there's still a holy grail out there to calculate an Einstein, to develop and construct an Einstein twistor string. And every time I look at it, it looks very hard. So, yeah, any help gratefully received.
Any more comments?
Okay, thank you very much. Bye.